Okay, let's get started. Welcome to the Richard Karp Distinguished Lecture. Before I introduce the lecturer and the speaker, let me say a few words about the Simons Institute. It was founded, as many of you have heard several times by now, in 2012, thanks to a generous grant from the Simons Foundation. And over the years, it brings together groups of researchers on specific topics with at least some angle in theoretical computer science, but with a window to the rest of computer science and beyond as well. So we connect theory with computer science, physics, math, biology, economics in a variety of programs. These programs bring the world's leading researchers together, but also young stars of the future. We have lots of fellows and postdocs who are just finishing their PhDs and graduate students here as well. The founding director of the Simons Institute was Richard Karp, and in his honor, we have this lecture series. And everyone knows the name, but in case you don't, Richard Karp is arguably the founder of the field of theoretical computer science. So he's made enormous contributions in almost every area of theoretical computer science, ranging from algorithms to complexity. Helped define the notion of NP completeness along with Cook earlier. So he's done many major contributions. So we have this lecture series, which brings distinguished people in the area of the current program who can speak to the broad audience of participants in the program. And today we have Sasha Rush, who is at the center of the LLM revolution at this point. Sasha is a faculty member at Cornell and Cornell Tech, but he also is at Hugging Face, which, among other things, tries to give you open source access to transformers and implementations of transformers and so on, so that we in academia can do some research on these kinds of topics and not just let industry do everything. Sasha is the winner of a number of faculty awards from almost every company that I can think of, all the big tech companies. So we can see that he's not in anyone's pocket because he's got awards from everybody. And he has a career award and several best paper awards at all the top, learning conferences as well as NLP conferences. So, and he's going to tell us about speculations on test time scaling.
I was thinking about your introduction, and maybe we should change our style. Like seeing Sasha there and he's standing kind of with humility. Start saying, yes, I'm great. I'm the best. We should adopt it. It seems to me. So say it.
I'm here. That's all I know. Today I'm going to talk about speculations on test time scaling. Say what you will about OpenAI, they make iconic graphs. For the last 5 years, this graph has kind of haunted my dreams. It's the thing I thought about every day. It's the scaling of GPT models and their performance on tasks they haven't seen before. In particular, this graph on Lambda is remarkable. This was a problem that I worked on for many years. It's extremely hard. It requires a language model to predict a word correctly that you could only predict correctly by definition of the task if you had looked back way in the past. It shows that learning a model just to predict the next word generally gives it this ability to do way better on all sorts of other hard tasks. But I'm kind of tired about talking about this slide. It's really been the kind of main and central driving force of NLP and language modeling research for the last 5 years. For that reason, I was really excited to see this graph. This is a graph that OpenAI released last month that describes some experiments that they ran on an entirely different setup. In this graph here, they maintain on one side the standard scaling curve that has come to dominate the discourse and much of the resource. This is a scaling curve we all understand. At this point, it's moved outside of research and into government policy, economics, energy questions about the world, right? But the other graph on this slide feels somewhat different. This is the accuracy on a hard task as you scale the test time compute of the model. We have an unlabeled x-axis that shows just getting larger in log scale at test time compute. And on the y-axis, we have the familiar performance curve, where we see the model getting better over time. Now, when we abstract it to this sort of graph, it seems somewhat, I don't know, abstract. But when you actually look at the problems they're talking about, they're pretty non-trivial. We're not talking about some of the things we've been seeing in the past, but we're seeing much more complex problems with much more challenging structure to them and much more challenging reasoning processes and chains. And so when we talk about trying to solve these problems and seeing that test time compute is able to get us there, it really changes the discourse of thinking about how these models work and where they're going in the future. I want to talk about this quote, as it's also kind of had a chokehold on how we've thought about these problems in the last 5 years. I'll remind people what Richard Sutton wrote in 2019. The bitter lesson is based on the historical observations that AI researchers have often tried to build knowledge into their agents. This always helps in the short term and is personally satisfying to the researcher, but in the long run, it plateaus and even inhibits further progress. And breakthrough progress eventually arrives by opposing approaches based on scaling computation by search and learning. For the last 5 years, we've really kind of focused almost single-handedly on this learning aspect of the problem. What people are talking about now is what search scaling will mean and what it will look like. And I think in many ways, this problem is much less well-defined and is really interesting to start thinking about, particularly as a researcher, because there are so many unknowns. In a previous lecture given at Simons early this semester, Noam Brown from OpenAI talked about his experience with search. The lecture is somewhat sparse, but it has lots of good hints that we'll talk about later in the talk about what might be going on. But I think one of the things he talked about most, and this is from a quote he posted on Twitter, is that the most important lesson is that I and other researchers simply didn't know how much of a difference scaling up search would make. If I had seen these scaling results at the start of my PhD, I would have shifted to researching search algorithms for poker much sooner, and we probably would have gotten superhuman poker bots much sooner. So he's talking about the kind of criticality of search in this process and how much it means to scaling models. He brings up a couple important and influential papers in his journey to this conclusion. One that has been influential for a while among people in this field, but somehow only has about 20 citations, which is kind of remarkable, is this paper about scaling laws for board games. This paper is an early example where they do a comparison in kind of a simplified board game environment, where they look at both the scaling for training these models, as well as adding additional search at test time. Likely, this training and search will look quite different than the training and search will do for language models. But the critical thing was plotting these on the same axis, getting a sense of how they scale together and the relationships between these two properties. Now, of course, they're pretty orthogonal in the sense that you can't really trade off training and test time. But if your goal really is kind of superhuman performance in something, it is a critical axis to think about. And this is the kind of thing that Noam Brown cautioned us to think about in our problems. The other paper he points out is this paper from OpenAI from 2021. This paper is kind of most famous in the community for introducing data sets for mathematical reasoning problems. But it also presents some really interesting results about how you might train models, both for generation and also for verification. Verification is going to be a main theme of this talk. And I'm going to try to be very careful when I'm talking about verification in the sense of formal verification versus the sense of learned verification, where you have a model that learns to kind of give you an answer. In this paper, they describe a process for training learned verifiers. They do this by generating from a model and then filtering out some subset of this data. They label these data points with human annotators to tell you whether or not you were correct in your answer. And then instead of kind of training a generator, they train explicitly a verifier to tell you whether or not it was correct. The aim here is that they want their generator to not memorize answers. They want it to search somewhat and maybe not be fully confident in what it does, but have the verifier try to pick out and figure out what's going on. The reason for this is because they wanted to draw these sorts of curves. This got cut off somewhat in my slide, but this is a picture from this paper. And what it's showing here is a blue line, which shows the performance of a fully supervised model, versus an orange line, which is a model that uses a somewhat weak generator, but uses the verifier to determine which is the correct answer. They're basically sampling hundreds of different outputs and using the verifier to decide what is correct. This is roughly the type of thing we're going to talk about when we talk about test time scaling, giving the test time model multiple choices to try to produce an answer and trying to figure out which one of these is correct. Okay. So before I want to begin, I want to kind of have some caveats. One thing I've been finding interesting about being a researcher in this day and age is that there are many different sources of knowledge. For this project, I read through a kind of large group of papers on this topic. I'm not actually an expert in this area, but I found it an extremely useful opportunity to get up on what everyone is writing. I also took the time to talk to many different experts in this space, both on Twitter and in real life, to get a sense of what they were thinking and what ideas they had. Finally, I'm going to include some rumors from various sources, but besides kind of watching like OpenAI propaganda videos, I don't have too much more to say on that side. So while I maybe promise you that I had some secret knowledge, most of what I'll talk about is public. And I'm going to really focus not on predicting what OpenAI did, but what we can learn about this area as a way to kind of get smarter and get a sense of how people might build these in the open source realm. So with that, let's get started. So I'm going to start by kind of thinking about this somewhat as an investigation. Let's first kind of look at the clues that OpenAI gave us about what's going on here. Now, it's always a little bit weird to just look at what comes out in corporate kind of non-peer-reviewed blog posts. But at this point, OpenAI has put out enough interesting information that I'm pretty fascinated by what they have to say. And I think their blog posts are really interesting when you dive into them. So I'm going to really just focus on two sentences from the blog post. This is the kind of main release blog post for O1. They say, our large-scale reinforcement learning algorithm teaches the model to think productively using its chain of thought in a highly data-efficient training process. So we have three clues from this sentence. The first is that there is RL involved. These days, the term RL has been stretched beyond limits, so it's hard to know exactly what that means. I'm going to take it just to mean that we're getting signal from some sort of verifiable problem. So unlike kind of training on the web, we're going to get signal here from something that has a right answer. Second thing, and we'll talk about this more throughout the talk, is that it does chain of thought reasoning. What this means is that the test time compute is going to take place in a single language model stream. So instead of kind of sampling many times at test time, we're just going to let the model talk to itself over an extremely long period of time. Finally, they describe this being data efficient. And I think this is particularly important. They're not saying it's compute efficient. They're saying that they do not need that much data to train it. Now, who knows what that much means at this day and age, but probably not tens of trillions of examples, because probably it's hard to get that many examples in practice. I'll make 3 other assumptions, and these are mostly from innuendo, from blog posts and videos. The first is that we're going to assume it's a single model. The model that just generates and produces the answer. There's no second model behind the scenes. I don't know why they need to do it this way, beyond just the fact that I think they're true believers, and they really want to produce a single model that does these tasks. I also think it would be pretty cool if it were true. Secondly, they're probably not writing down a bunch of expert examples and training on them. They're collecting a bunch of expert feedback, but not explicit examples that people wrote down in practice. Finally, I'm going to assume that to first approximation, most of the behaviors we see are learned. So I don't know exactly how to define that, but we'll say something from a data process as opposed to kind of hard coding them in. So let's review a little bit what chain of thought means. So explicitly, this means that the model is going to generate intermediate steps in the process of producing its answer. I'm going to use a very simple example throughout the talk. I'll have a red color representing a question asked to the model. I'll have green colors representing the intermediate chain of thought that gets generated. And I'll have orange colors for the answer. In this particular example, we see 4 steps of a chain of thought leading to the answer to the problem itself. I say there are 4 steps because each of these lines represents roughly 1 step in the process of solving this problem. This method has kind of dominated a lot of prompting research over the last several years. It's thought to make models, well, a little bit better, but certainly not to the extent of just being able to plug it in and do the kind of things OpenAI is talking about. Here's the second sentence I think is important from the blog post. They say O1 learns to hone its chain of thought and refine the strategies it uses. It learns to recognize and correct its mistakes. It learns to break down tricky steps into simpler ones. It learns to try a different approach when the current one is not working. So I think it's hard to quantify exactly what these mean, but in the blog post, they provided several examples that are extremely long and provide some sense of what this might be referring to. So I think it would be worthwhile to spend a couple of minutes looking at these examples. Just to make it clear, these are chain of thoughts that the model is using to solve challenging problems. In this example, it's using the chain of thought to solve a coding problem. This is not part of the final answer. It's part of an extremely long, think like thousands of words example. And what we see is that it's doing some sort of outlining. So it gives this whole outline with multiple steps about what it needs to do. These steps describe what's kind of required in the problem and what's needed in the process of producing it. Here's another one. Here we see something akin to planning. It says, first, do the following thing. Then option 1, try this. Then it asks itself a question, do any letters match? Writes it down the next step. It also does something which they mentioned in their blog post that's quite interesting. It says, given the time constraints. They refer to this as it kind of knowing how much actual compute it has available in terms of solving this problem. Another behavior we see is backtracking. So here, it's written down a mathematical formula. On the next line, it says, wait, actually, this may not help us directly without specific terms. It then goes on to a different aspect of the problem. This is certainly not behavior we see in models today. It's really fascinating kind of meta strategies for trying to produce answers to these problems. And then finally, we see explicit self-evaluation. So we have option A, because appetite regulation is a field of staggering complexity. And then it says, is this a good explanation? Question mark, and then, This is in the chain of thought, actually looking back upon what it had done previously and trying to produce an answer. Now, I'm not going to provide explanations for how this works. I think this is beyond what we know in the open source community. But I want you guys to keep these in your head as we talk about the more abstract ways that these problems might go about being solved, and think about how these behaviors may or may not emerge. Okay, so let's just summarize. Chain of thought provides test time scaling. Actual chain of thoughts look kind of like classical search, planning, outlining styles. And we know that there's some sort of reinforcement learning going on to induce this behavior. Cool. So now what I'm going to do is pivot to a more technical background. I want to first introduce some shared notation that people think when talking about these sort of problems. And then I'm going to go through 4 different suspects for how we think O1 might be working. Let's start by just defining our terminology. So when we talk about chain of thought, we have this idea that there's a question and then some sort of chain and then a final answer. We're going to think about this as basically being a kind of latent combinatorial variable. The chain could be arbitrarily long and have many different steps in the process. Before we talk about any sort of reinforcement learning, I want to talk first about what we can do in this sort of latent variable model. So let's define our terms explicitly. We have a problem specification X. This basically tells us what we need to solve. And then we have this chain of thought. So we're going to think about the chain of thought as being at the step level. So we're going to abstract away from the fact that this is a language model and just say that the model gives a probability for a next step in the chain. We'll say that there's a maximum T number of steps in the chain, and these we have to produce latently. Finally, we'll talk about Y being the final answer to the problem, being either the last step in the chain or just some answer that you provide. So given this framework, there are a couple different moves we can make. The first is what we do today. So this is a form of ancestral sampling. This is what happens when you say, ChatGPT, produce an answer to this problem. It'll just generate a bunch of steps, and it will generate a final answer. We can think about the amount of test time compute that we're using as some T, which is a max value, although it can stop early. We know that this provides some value, that there's some benefit from using T test time compute, but that value is kind of marginal and it stops after a certain limit. The other strategy that people often use as a baseline for these models is some sort of majority voting procedure. This is also referred to as self-consistency. And as we'll see throughout the talk, there are about 12 names for every different method that gets used in this space. In this strategy, we're going to basically do Monte Carlo sampling. We'll sample n full chains, and then we'll have some way of determining what chains refer to the same answer. We'll have some sort of normalization process at the end, and then we'll just do majority voting. This is a way that we can go from T steps of compute to n times T steps of compute. And this yields a predictable benefit on top of the base model. Cool. The next assumption we'll make is that we have some sort of automatic verifier during training. We'll think about this as a binary function that takes in the chain and the answer and just returns 0 or 1, whether you got it correct. You can think about this as being a kind of regular expression for a math data set, or maybe something more complex like a theorem prover. You can think of it being unit tests for code that tell you whether your answer is right, or you might think of it as kind of test questions for something like science. This will be our base assumption throughout the rest of the talk, that we have access to this. Now, there's a certain question about whether this is a fair assumption at all. I noticed in OpenAI as talk, they're kind of unclear about this. They really kind of emphasize that they want to learn the verifier as opposed to using automatic ones. And they talk about this being an important problem. They're very interested in this idea that you need to learn an extremely robust verifier. And they have some graphs in their previous papers that show that if your verifier is not robust enough, models will exploit it and actually do worse with more test time compute. So in this graph here, they show that it actually decreases with more test time compute if your learned verifier was not strong enough. My speculation is that there was a huge and expensive data collection effort in order to learn a really strong learned verifier. They probably have access to that internally, and it's very beneficial for their processes. That being said, that's not super interesting for this talk. So I think it's fair for us to say we get to use an automatic verifier, and who knows what they did internally. So for the rest of this talk, we'll assume at training time, we have access to verification. Great. So we have access to a training time verifier. We can do things like rejection sampling. This is often called best of n sampling in this literature. For our take, we'll say they're roughly the same. So here we'll do Monte Carlo samples of n chains. We'll then check which ones are correct, and we'll throw away the incorrect ones. So in my notation on the right-hand side of the slide, I'm kind of showing these chains, and I have the verifier as a little square at the end. I'm thinking of chains that end up in the verifier kind of box as being correct, and the other ones being incorrect. Here, this is not exactly what we have in language, but I think it's a useful kind of visual schematic. Cool. The other thing we can do with verifiers is that we can do Monte Carlo rollouts. So for this setup, we'll assume that if we're at any given step in a particular chain, in this step T, we can do Monte Carlo rollouts and check how many of them result in a correct verified solution. So computing this expectation requires additional cost, but gives us a way to check if we're on the right path for the problem. Cool. So those are the tools we have in our toolbox. But our goal is not simply just to use a verifier. Our goal is to learn from it. So we're going to think about this as a problem of maximizing the likelihood of producing verified solutions. Here we'll think about this in the kind of extreme case as marginalizing out over every possible chain of thought. This is, of course, extremely intractable, and we can't really hope to train in this sort of setting. So all of our procedures are going to be some sort of approximation of avoiding this full marginalization by thinking about ways that we can do better search during training and get better signal to do better on these problems. Great. I'll make one other note, which is that for this talk, I'm mostly going to not talk about reinforcement learning. The specific way you do reinforcement learning is pretty critical for these problems, and it determines whether your approach is stable or unstable, whether it converges. I think all of these algorithms have kind of a simple form and then a reinforcement learning form. I'm mostly going to talk about the simple form just to avoid these problems. One thing we've seen is that for areas like RLHF or other aspects of training, companies develop really nice and complex full-on RL systems, and the open source community mostly uses some of the simpler batch versions of these algorithms. This has been an interesting topic to follow, but I think it's somewhat orthogonal to the question of kind of how you do the search for these problems. Just be warned that if you're into some of the RL stuff, I'm going to kind of elide most of it for the rest of the talk. Okay. So one more quote from OpenAI. When training a model for reasoning, one thing that immediately jumps to mind is to have humans write out their thought process and train on it. When we saw that if you train the model using RL to generate and hone its own chain of thoughts, it can do even better than having human write chains of thought for it. That was the aha moment that you could really scale this. Kind of a further emphasis that the kind of first thing you might think of just writing down lots of solutions to math problems is not kind of the way these things are proceeding. We're really trying to inject information from the verifier back into the model itself. So for the last half of the talk, I'm going to talk about 4 different suspects for what we think might be going on. These group together dozens of different papers each, but I think they represent 4 orthogonal directions, kind of getting more complex as they go for how one might get this behavior to work. We'll start by talking about a kind of guess and check style approach. Our first suspect, which we'll call guess and check, follows a kind of 3-step procedure. In this procedure, we'll first sample n chain of thoughts. We'll then just do rejection sampling, which ones actually hit our verifier during training. And then we'll train on the good ones. Roughly the procedure. There are dozens of papers written about this kind of thing, and there are a lot of details. But roughly, this is the kind of thing we're thinking of doing. There are many different ways of formalizing this. The one on partial was described in a paper called REST-EM. They think about this as a form of expectation maximization with rejection sampling. We're going to have an E step where we sample n possibilities. We'll collect them all in our kind of verified set. We'll think about this as giving us some approximation of the posterior distribution. And then we'll use that approximation as what we train on in the next step of the process. So this gives us a way of thinking about this within the latent variable framework as what we're doing in this problem. Now, of course, this kind of has a batched version of this problem, but you can think about online variants or kind of stochastic variants for these approaches. Okay, here are 6 of the dozens of papers that do something like this. In the NLP field, for many years, this was known as self-training and was used for various tasks like parsing and machine translation. I think all these papers add a kind of new information and interesting ways of how this goes about. Cool. And yeah, this works. You can show that compared to a baseline that uses something like self-consistency, doing some sort of training like this, using a kind of guess and check filtering, will improve upon your system. The results are pretty promising, and I think all the papers have something like this as their baseline to understand how you might get some of the further forms of scaling. Cool. I'll mention also that, again, the verifier here is only around during training. So we're using it basically as a way of constructing our training data set. You can use samples from this form to also try to get some sort of learned test time verifier. So you can kind of take the examples that you've produced and try to train a model that can predict which one of them will actually be verified. This gives you some way of getting a verifier at test time that you can maybe search against or run against your chain of thoughts. That being said, that is kind of somewhat goes against the assumptions we've been making so far that this is maybe a single model at test time. So start with that. Is this O1? Is it just a matter of kind of sampling lots of outputs, filtering them, and training on them? In some ways, I really like this solution. It's extremely simple and scalable. OpenAI has kind of amazed me again and again in taking methods that were pretty straightforward and just showing that if you have many orders of magnitude, more data and annotations, they work really well. The positive results for this are really interesting. And if we could scale it, you might start to see interesting things. The cons are that in the public literature, I see like slight benefits from this approach, but nothing that hints that it's like learning magically to make plans or learning magically to backtrack. It would be a really shocking and interesting result if someone showed the emergence of that kind of capability. Now, that being said, the models we're working with in the open source are much worse And so maybe we just are not seeing that due to the models we have access to. The bigger problem to me seems that this is just kind of an inefficient process. We're assuming that rejection sampling finds any solution. But for hard problems, that's really unlikely, right? It's probably going to, no matter how long we sample, never find anything in practice. Okay, so let's move on to a slightly more kind of custom solution. So we'll call this one process rewards based on the terminology that OpenAI uses. So here is how it works. So during chain of thought sampling, we are going to try to find the rewards that we have. Give me one sec, sorry. Okay, cool. We're going to basically look at a kind of a partial reward for our chain of thought so far. We're going to use this to kind of steer our model to see if it can find a final answer. When it's done, we train both on the successful chains, but also on how good you did at hitting these intermediate process rewards. So let's define this formally. We'll have a function, we'll call it R. It's able to look at a prefix chain of thought and tell us how good it's doing. In the OpenAI terminology, they refer to the early model as a PRM, a process reward model, and they refer to an outcome reward model as an ORM. In this graph here on the right, they demonstrate that utilizing kind of this early feedback from a PRM is able to improve the rejection sampling process significantly. So this one here is majority voting. This one here is just having an outcome. And this one is being able to kind of look at the intermediate solutions and give them rewards. This was a kind of paper they put out demonstrating that this approach could be effective at helping rejection sampling. So how do we get these rewards? In the terminology that we're describing so far, we're going to assume that we can get them somewhat automatically. So we're going to do this by producing a chain and then rolling out from the position in that chain. From that, we can get an estimation of the expected value of that part of the chain itself and train on it in order to get something like a process reward. Now, I'll note that this is how people in the open source community do it. It's likely that for OpenAI, this is being collected with actual annotations from users or experts in the field. But how does this relate to this idea of it being a single model? It seems a little strange that you'd have to train this separate model to tell you how well you're doing in the process itself. So recent work has explored the idea that maybe the process reward could be a language model itself. The idea is something like define R as a large language model. This large language model is simply conditioned on the chain of thought so far. And its job is to tell you whether the process so far is good or bad. You can define that as outputting a scalar value at a given step, or you might define it as using natural language in order to describe how well or how badly you're doing. If you might be able to do this, you get chain of thought in the process verifier itself. You can imagine something that looks more like the chains we saw earlier in the talk, where we kind of trade off between generating more solutions and checking those solutions as we go. So several recent papers have explored this idea, but actually kind of building the full end-to-end system is still kind of an open and interesting question. One thing people have been able to do is build open source versions of these learned process reward models. So for this paper called Math Shepherd, they use rollouts on math problems to train a model to tell you how good your process is so far. From these rollouts, they're able to improve upon methods that simply look at the final solution of models and improve the percentage of problems solved in math problems. This seems to be one area that is particularly promising. People know how to do these kind of trained rollout models quite well. and being able to run them on various different problems may produce very good process reward models to use. Cool. And as I mentioned earlier, like to actually incorporate this in test time, you might imagine something like this actual chain of thought here, where the model stops and says, is that a good explanation? That last step is in some sense part of the process reward model, and you're kind of accessing it at test time. But it's also part of the same chain of thought. So by merging them, you might get something like a single model that has both these properties. Cool. So is this O1? So it seems like there's results so far that it's effective. And it removes some of the challenges of a kind of full learned verifier. You have this nice kind of simple back and forth step. You haven't had to do any sort of complex tree operation. You just really focus on learning a really good process reward model, and then you use RL to do the rest. Still though, it's not clear if this is enough for full planning. And we don't have all the details down to really combine this into a full approach. That being said, given what OpenAI has said, this is the closest to what they seem to be describing. They don't seem to be talking about a lot of other crazy things. They really are kind of talking about something like this and publishing papers in this space. So from a betting standpoint, this is kind of closest to the information we have. Okay. So now let's talk about something a little bit more combinatorial. Let's imagine we want to do full-on search. This has really become like part of the way we think about areas where RL works. The AlphaGo, AlphaZero, and MuZero paper are extremely influential as papers that showed methods to go from learning on trajectories to learning on full-on self-play. And I think for that reason, a lot of people are excited about the possibility that maybe a full-on AlphaZero is behind what's going on here. At a high level, the way these methods work is they alternate between doing self-play and then learning on the trajectories from self-play. By going back and forth, they're able to get steady improvements on the model. And then adding additional test time scaling improves the model further. One recent work was AlphaProof, which was released earlier this year. Sorry, the citation is slightly wrong. And when they say in their blog post, when presented with a problem, AlphaProof generates solution candidates and then disproves or proves them by searching over possible proof steps in Lean. Each proof that was found and verified is used to reinforce AlphaProof's language model, enhancing its ability to solve subsequent, more challenging problems. Here we're talking about really like full-on search and improver system, using that to update a language model itself. So here's the process. We do self-play with exploration. We label final outcomes. We train and guide our generator. So I'll go through this quickly. I think you can formalize this in certain ways, but it's less important. What's important is thinking about how this might actually apply to language modeling. So we'll follow a paper that kind of uses an approach known as beam search. That's very common in language models. And it's going to use something like a guide or the process reward model to tell us how good we're doing in the process for our answer. So roughly, it looks like the following. So here on the right, we have our chain of thoughts. We're doing tree search, where we keep what's called a beam. So 4 different full chain of thoughts at each step that we think are quite promising. And we weight each of these steps by how far they are from the final answer. So we have some guide that tells us how close we are to producing the right solution for this problem. This is an algorithm that can be scaled very well with language models. It allows us to do pretty effective search at trying to find chain of thoughts that lead to a solution. You can also do this approach combined with rollouts. So maybe you have a learn guide and are also doing rollouts during training. This is something that was common in the AlphaGo style of work. So what does this look like in terms of animation? At each step, we're going to just move forward, keep around 4 chain of thoughts, and use rollouts to tell us how close we are to the final answer. We can then collect both the rollouts and the chains and train models on them. And people have showed this works really well. So in this paper called V-star, they do a method like what I described. They're able to both learn a guide and also do search for these problems. And they showed that this gives a significant improvement over the guess and check style method. Now, this requires more training time compute and more infrastructure, but maybe that's worth it in order to get better models, given that we don't have that many training problems to work with. We can go even further and think about how we might fully implement AlphaGo for language modeling. Several recent papers have tried full-on Monte Carlo tree search for language modeling problems, where they run an algorithm that looks like the following. We're doing a full-on Monte Carlo selection, expansion, rollouts, and backprop. This is treating language like it's a game like Go and just playing that game. One key step that actually I was confused about when I first looked at these problems is that in language, there are infinite moves at every step. Whereas for Monte Carlo tree search, you need to have a limited game. In order to get around this problem, they sample 5 next steps for every chain of thought and just kind of fix them in time. So that really kind of treats language as if it had 5 steps in the process. And this is based on some tricks from the Mu0 paper. So here's an animation for what this looks like. So we're going to first do a selection step. So that'll be in yellow. So that tells us which we want to expand next. We'll then expand, and then we'll roll out. And we keep on doing this process over time. Cool. And the kind of main benefit here, the main hope to get properties like AlphaGo, is that you're doing exploration as well as search. So you might try out moves that are slightly different than what you've seen to try to find an answer to these problems. Now, that all being said, I don't want to get too excited about these methods. While these kind of MCTS approaches were kind of really critical for the development of these techniques, they seem to be quite complex. And actually, there aren't too many results in the literature yet showing that they work at all. So while simpler things like beam search can be helpful, I'm not sure we have something that really demonstrates that MCTS is worth all the extra effort for language. So I think this extra cost of maintaining open states or having extra algorithmic complexity does make the problem much more challenging. I don't really want to get too far into some of the rumors about this kind of approach, but I think people think probably it's simpler than this in practice. I think that's where we are at the moment. Cool. One more suspect, and I want to wrap up a little bit by talking about where this all leaves us. So the 3 steps so far have really focused on how you add more search to the training process, how you do better rejection sampling, how you do better MCTS. But I kind of have this feeling that game playing is pretty different than language. That in game playing, you can explore a kind of wide set of different moves. But in language, particularly when you're talking about some of these kind of meta planning strategies, there really is quite a large set of possibilities. And so arguably, the type of exploration you need is not exploration of the tree. It's getting the language model to produce different and varying sort of strategies in this process. So the challenge here might not be just doing more tree search. It might be getting the generation to kind of proceed in a way that looks more like what you'd like. So we're going to think about this in terms of learning to correct. So here we start with a failed chain of thought. And then we're going to just search for successful corrections. If we can do this well, we can train on the full chain of thought and actually have the model do self-improvement. Now, I would say of the 4 of these, this is the hardest one so far. A lot of people have thought about this problem, but we don't have a nice off-the-shelf way to get models to correct or backtrack. So one framework we can think about this is in terms of self-correction. So in this paper, they tried to find pairs of chain of thoughts that were similar to each other, but one was wrong and one was right. So in this example, one reaches the goal and the other fails. You can then put these back to back and try to take a model to learn to improve from one to the other. Gives you some good results, but it has a bunch of challenges. So one challenge is that the model tends to just collapse. So it could just generate the right answer and pretend it didn't even see the previous one. The previous one is wrong. So in some sense, it provides almost negative signal to producing the right answer. The other problem is that it might not actually look like what the model is generating in practice. You need to make sure it's actually seeing mistakes that it would make and improve upon them. So people have begun to think about other sorts of reinforcement learning techniques to try to improve correction. So a kind of general approach that people are utilizing is to allow the model to go and maybe go off path, and then think about doing reinforcement learning instead of from the beginning, but from that position. If you can do that well, you can maybe learn to backprop, maybe just to the correction part of the model, to try to produce a better answer to this problem. But it is really tricky. You have to make sure your first model is not very good, so it produces wrong answers. And you have to make sure it stays kind of similar to what you'd actually see at test time. Cool. Let me just make one more point, because I'm running out of time. I think the thing I'm very excited about, and I think a lot of people are excited about, is thinking about how you take this correction process and actually getting it into a tree itself. So if you can kind of do this search and kind of hierarchically find all the areas where it failed, you might be able to learn a type of correction that you could actually do multiple steps of correction upon. So from this paper, and actually I think the author is in the room, so I'll try to not butcher it too much. We're going to do a kind of tree search to try to find an answer to the problem. We're going to find what the optimal chain of thought was. So in this example, this chain here is optimal, but we're not going to use that one. Instead, we're going to kind of walk through the tree to produce a new chain. This is the chain down here. And this is a linear left to right chain, but it has things like backtracking and kind of self-correction built into the chain itself. So if you can do that, you can kind of merge the kind of AI search going on during training into a single chain that has those properties with it. Now, again, this is early times. We haven't demonstrated this for real language problems, but I think it's an exciting approach and a way that you can kind of get these properties from the tree into the chain itself. Okay, cool. So I think this is really exciting from an open source point of view. It does require us to build in some of our knowledge into the search process itself. So in the sense of kind of building structure into the problem, it does differ somewhat from the just purely learning or training-based approach that OpenAI seems to be hinting at. They do use the terminology that the system learns to search. And so whether that counts if you build this in or build it into the reward model is unclear. This also would require some sort of complex process and require writing down a lot of the search strategies that you might have. That being said, the fact that their chains actually look like search is an interesting property. Cool. So I think at this point, I'm out of time. I have one more slide if you give me a minute or two. So these are kind of our four suspects. I think this area is extremely interesting. For the last many years, it's been very clear how things work. We train transformers, we train them bigger, we want them to be faster. This space is pretty fresh, and there's a lot of interesting questions to be asked or to work on. So one thing I really want to encourage everyone who might be listening is to think very hard about how we do this replication. I think it's very critical that we have open source versions of these models. And I think it's really critical that we think about some of the open source systems challenges in replicating large scale RL systems. One thing I'll note is that it might not be exactly the same model. Like maybe the version that everyone ends up using over the next couple of years, it might look pretty different than whatever is being developed internally. But I think the fact that it exists and it's available is worth kind of thinking about how we reach that point. Finally, I think I thought about a couple areas that I'll just mention briefly that are like entirely different, that get opened up by this kind of approach. So one thing I'm extremely excited about is moving beyond this idea of only thinking about abilities as being emergent. In these systems, we have the entire chain of thought. Whether we believe it or not is an open question, but it's really writing down English versions of what it's doing and what it's proceeding with. That feels very different than the kind of black box opaque models. I'm also extremely excited to be moving on from prompting. I think prompting was like a really bad thing that the research community got into, and I really think it'll be really exciting for it to go away. So with these sort of models, we're talking about writing down specifications and letting it do search for them as it goes. Another thing I've been thinking about a lot recently is that evaluation needs to be way, way, way harder. I think we got into a local optimum where the evaluations were designed for the models as opposed to just writing down crazy problems. So like one thing I've been working on is just really hard coding evaluations. Like coding is an amazing area where like you can actually check if what you're doing is correct. And I think I've been inspired by some other people in the audience as well, just to think about that as a problem. Like, how do you think about problems you might not be able to solve, but can write a unit test for? Cool. And then I think in the same note, thinking about some of the systems questions involved in these problems are quite interesting as well. We're not just talking about it being faster to save more money, but we're talking about it being faster to actually reach new orders of magnitude in terms of reasoning. I think that's a really interesting area, particularly for inference time compute. So with that, I'll thank you all, and the slides are online. Yeah.
Thank you so much. That was an excellent talk. So to what degree do you think the generator, verifier, and or reward model, whether it's process or otherwise, need to be co-trained, co-designed, or kind of like modularly trained, and then some lightweight fashion sort of like fine-tuned together?
Yeah, it's a good question. I purposely avoided it, but it seems like one lesson from the last couple of years is that having things be as on policy as possible is pretty critical to these things being stable and useful. So even if you're doing things that look like kind of batch training, kind of doing it iteratively or getting more data that is kind of from the particular generator you're using at a given point of time seems to be critical to the process. So yeah.
Hi, nice talk. Thank you. You're in a position to evaluate what OpenAI means, and there have been recent attempts to characterize what standards for OpenAI research should mean. Do you have any opinions about those statements?
Yeah, I do. It's somewhat outside the scope of this talk. I think we all agree OpenAI does not fit any of those terminology. I think the question about Llama is an interesting one. I would love to encourage them to continue doing what they're doing. Llama has been such a valuable resource to the community. That being said, I do agree that this is a hard problem, and that clearly it's something different than open source for software. I'll say the following. I have a YouTube channel, and I have a bunch of videos from a workshop I ran last year called OSGAI, which was a bunch of open source leaders talking about these questions. And a lot of them had really interesting and nuanced views on exactly this topic. So you can find that online.
Great talk. It's a two-part question. So first, you talked about chain of thought and a way of increasing the test time compute, and largely that's decoding tokens, right? Another
entirely. For this model, it's entirely that.
Exactly.
Yeah.
But another related method for test time compute is in-context learning, which entirely is context, the prompt, right? Can you comment on that, versus decoding?
I think my comment will be that in modern systems, the pre-fill phase of like reading X has gotten extremely optimized. And but it's also conditional. So this idea of really like latently producing more information almost has to be this feedback where you produce the tokens and then feed them back in. So I think it's an important practical question of how to expand to longer lengths, but I think it's unlikely that that's going to lead to this kind of feedback loop that we're hoping to see in some of these test time problems.
So you mean in-context learning can only do so much? It's not going to be as effective as decoding?
I think it's really important. We should figure out a way to get 100,000 data points in the context of models and use them to produce outputs. Really cool problem. I understand that problem much more than I understand this problem, right? It's like a deep learning question of how you get them in, how you process them, how you make the model better. But I think it's somewhat different than what's going on in these kind of generate and process problems.
Second question. I'm working for a company that is making a transformer chip that make inference that 20 times faster than current GPUs.
Yeah.
In your opinion, what are the uses of this kind of future system that's super fast?
I mean, this is your thing, right? I mean, these things are literally scaling by that. If you can make them 2 orders of magnitude faster, that's like going from on this graph, like right. I mean, if you can go from here to here, that's nothing to a huge amount of solving, right? Now, that being said, I don't know the business uses of this. So maybe most of the use is just getting it to respond quicker to easier questions. But this is a very exciting combination of ideas.
Thanks so much for the here.
Okay.
I had a quick question. You briefly mentioned that the models might ignore the mistakes, right?
Mm-hmm.
Even if you do contrastive examples, like they might ignore what they should not be doing or the backtracks. I was wondering if you had any ideas in general of how to teach models what not to do, because it's really hard. Even if you tell them don't do this, or if you try and train on that, because of how the objective works, they would not operationalize like what it means to not do something as opposed to do this. So I've seen that just telling models what not to do is much harder.
Mm-hmm.
Do you think there's a scaling law to it that like, oh, if you just 10 times more data would help it? Or is there other ways of doing that?
That's a really fascinating question. I'm actually not an expert in this area. This is from the SCORE paper. It's a very nice paper. It discusses this topic in detail and proposes some approaches for trying to solve it. The approaches are mostly on the kind of RL sampling side and less on the semantic prompting side, as you described. But it does kind of discuss some of the issues that come around in that space. One thing I'll also note is that it seems like open source models are much worse at this than models like Anthropic. So there may be other or different approaches to get to self-correction or correction in this space.
I am a little curious about your initial thoughts on how these various methods might perform differently if the verifier is noisy.
Yeah, so I had one slide about this, which is this slide, this one here. So this is showing explicitly what happens when the verifier is noisy. And the x-axis is the number of basically samples you take, and this is the solve rate. And what they're showing is that, and this is actually from Noam Brown's talk as well, he particularly noted that as you go to 800 samples or 3,200, you get worse. So this is showing that you're hitting points in the learned verifier where it's giving the wrong answer. So kind of outside the region of like where you can trust the verifier. And so you start actually getting failure cases from it. And so I guess one argument is you need to expand that region as much as possible, maybe with supervised data, or you need to be really careful about not just trusting a learned verifier, but also having some notion of what confidence you think it will have on your particular output. This gets explored a lot in kind of the offline RL literature of like when you can trust it to provide you a good signal.
Thanks for the great talk. So I wonder, you presented these 4 different options as sort of distinct. And I wonder, what do you think about the relation between them? So for example, to me, it seems that 2 is a superset of the first one. And 4 and 2 seems to be able to coexist. So I just wonder, like, what do you think about the relation of them, and can any of them actually cannot coexist?
Good question. I think they all coexist. And I think it's entirely possible that to do the last step, you need all the previous ones. I think the reason I drew a distinction was because when I first came to this space, I had an entirely different ontology. And I found it interesting that throughout this process, I kept on changing what I thought was maybe important ideas. So I wanted to kind of settle down upon one way that I was thinking about it. The other is that related to the kind of bit or less in question, I think they go from assuming less structure to kind of assuming more, where I think the last methods are kind of like, there's an idea of backtracking, it exists, we should have the chain of thoughts follow that. Whereas the first method is just like, go wild, let the language model run, right? So that's how I was thinking about the 4 of them.
Hi, great talk. Can you go to the OpenAI plot of the test time scaling plot? Yeah, in the beginning.
That's the first one.
Yeah. So in this plot, I think one question is, how do you think they control the length of the chain? It's like all the technique you have been talking about is how to have model generate those high quality chain of thoughts. But to be able to produce this kind of plot, you sort of need to fix a problem and let it to think different amounts of time. And that feels extremely natural with approach to like a majority vote or like having some external verifier reward model during test time.
So the assumption I'm making, and maybe this wasn't clear, is that this plot is purely ancestral sampling. They're just saying, solve this problem, you have 64,000 steps, go. And then you just literally sample from the model. And maybe the only thing different is that you change the prompt slightly of how much you tell it has. Now, I know that's a little crazy that it can like go for this long. But one of the things they noted was that these approaches only started to work once they had really good long context models that kept this consistency. It really is just sampling for thousands and thousands of steps.
Yes, thank you for the answer. So like there is a famous tweet thread, like people just prompt O1 to think for different amount of time to replicate this plot.
Okay, cool.
Yeah. I think you know the plot I'm talking about, but the quality of the line is very different from this one. Like
they made no claim that the model they were serving in production is the same as this graph.
I see.
So this they probably have all sorts of things on the production model that are different than this one here.
Okay, thank you.
Oh, yeah. So we've discussed this a bunch before, and you know my personal opinion is O1 is kind of a combination of a few of these things. But I think the biggest bottleneck.
Wait. Let's just for the video stream. Why don't you just give a sentence of what your guess is right now? Yeah.
Yeah. So my guess is there is a very large PRM that's trained on very large amounts of human step-by-step annotated data. That PRM is used to generate search traces through some heuristic or through some search approach, where it's A*, or MCTS or breadth first or something like that. Those traces are used to train a model basically in a stream of search way, which is then further fine-tuned with RL. So that's been my personal opinion for a long time.
Sounds great.
But I think the biggest bottleneck to research on those ideas has actually been data. So we have, we can get certain amount of data that comes in a more easily verifiable format where the things end in like /boxed, and you can check the answer or not. But how do we move beyond that, where we actually have like difficult open-ended problems, where we do need to check step by step, where we do need to verify an entire plan or entire solution without actually having the access to literally billions of human level annotations? How do we do that in the open source community? Where do we find those type of data?
It's a really good question. Just for the record, the speaker was surrounded by almost all the authors of the papers he mentioned. So he might have been polite, so they didn't beat him up. I love that question, but I'm also like, there are so many people fascinated by this topic who want to work on these things right now. The open source community is really thriving in this space. And to have all that stuff plus companies like Facebook that seem to be just contributing things or putting out data is really useful. I think we should all sit down and write verifiers for everything. Like we should just have open source verifiers for all sorts of problems. I think we can get a long way with distilling solutions from some of the models we have, or maybe some combination of distillation plus verification for these problems. That was very helpful in getting really good RLHF models in practice. But also, I don't know, I don't hate the idea of people like verifying math problems and putting them online and building these data sets. I mean, maybe you think that's like too long to wait, but I think it's worth doing. Yeah.
Yeah, my question is, you propose there's 4 type of approaches to achieve some sort of reasoning. And if we look, let's say 5 or 10 years out, which one of this is the most scalable according to the video lesson? Because it does seem that a lot of this search type of algorithms, it's not exactly too scalable. It doesn't really scale with Moore's law, doesn't scale with compute. It's just versus, let's say, get a whole bunch of train of thought and just train that into either a verifier or a PRM or ORM, et cetera, et cetera. Like which one of this is actually scalable and simple enough and scalable enough?
I want to be careful that we don't like overfit to how training scaling happened. So for training scaling, it had to be so fast because we had to fit the entire English language for history of the world in it, right? Or all the languages for the history of the world in it, right? The setup here is pretty different. There's probably only a fixed amount of data we have access to. And scaling has to be more horizontal, of like more tree search or more structure. And it's unclear to me at the moment how bottlenecked that is by, say, calling the language model versus calling a verifier versus other things. And so I think the kind of systems questions here will look slightly different than what we've thought about in the past. So I don't, like, for instance, this beam search with verification method, I think is extremely scalable. And I think you could do that really well. The questions that come up are more like how you pass the gradients between different on-policy search algorithms on different servers. And this is the kind of thing I think companies like DeepMind have been thinking about for many years.
Thanks, Sasha.
He mentioned that one of the things that people do is just linearize everything and just shove into language model, and it just magically works.